Every time you send a prompt to an AI model, you get billed for something you never actually see. Not words, not characters, tokens. And the same exact prompt sent to two different models can produce a completely different number of them. I tested this. I sent the phrase "Hello World" through the Anthropic API, and the usage report came back with 11 input tokens. I sent the identical text to Gemini, and it counted 4. Same prompt, same 2 words, different bill. That gap looks like a mistake until you understand what's happening under the hood. And once you do understand it, a bunch of other weird AI behavior suddenly makes sense too, including why these models famously fail at counting the letter R in the word strawberry. So stick around, because this connects to more things than you'd expect. A token is just a number. That's the whole secret. Every model ships with a giant lookup table called a vocabulary, and inside that table, every common word, every chunk of a word, and every individual character gets assigned an ID. The word hello might be entry number 24,912. The chunk ing might be entry 341. A single comma has its own entry. When your text hits the model, the first thing that happens is a conversion step. Your prompt gets chopped into the biggest pieces the vocabulary recognizes, and each piece gets swapped for its number. The model never sees your text at all. It sees a list of integers, does all its computation on those integers, and then spits out more integers, which get converted back into text at the very end. So when people say a model reads your prompt, that's not really accurate. It reads numbers, text in, numbers, math, numbers, text out. You can watch this happen yourself, and I want to show you because it makes the whole thing click. OpenAI publishes their tokenizer as an open source library called TikToken, and there's a free playground on their site where you can paste text and see the exact splits. I'll type in, "The quick brown fox jumps over the lazy dog." That sentence is 44 characters, and it comes out as 10 tokens. Each common word gets 1 token because these are frequent words that earn their own vocabulary entry. Now watch what happens when I type a made-up word like Flurbington. The tokenizer has never seen that word, so it can't find a single entry for it. Instead, it breaks it into fragments, herb, ington, whatever pieces it can match. One fake word just cost me 3 or 4 tokens. Keep that in mind, because it explains a lot about pricing later. Okay, so back to the mystery from the start. My Hello World prompt hit 11 tokens on one provider and 4 on another. Part of that is hidden formatting. When you call a chat a PI, your message gets wrapped in special structural tokens that mark where a message starts, where it ends, and who's speaking. You pay for those wrapper tokens even though you never typed them. But the bigger reason is that every company trains its own tokenizer on its own data, so every model has a different vocabulary with different entries and different splits. There is no universal standard. A token on GPT is not the same unit as a token on Claude or Gemini, which means comparing per token prices across providers is honestly a bit misleading. A provider with a less efficient tokenizer can advertise a cheaper rate per million tokens while quietly burning more tokens on the same text. If you're picking a model for a production app, the real number you care about is cost per task, not cost per token. Now, let me explain how these vocabularies get built in the first place, because it's a surprisingly simple algorithm. The standard approach is byte pair encoding. You start with a vocabulary of just individual characters, then you scan a massive pile of training text, terabytes of it, and you find the pair of characters that appears next to each other most often. Maybe that's T followed by H. You merge those into a single new vocabulary entry, severed. Then you scan again. Maybe TH next to E is now the most common pair, so you merge those into the. And you just keep repeating this, merging the most frequent pairs over and over, tens of thousands of times, until you hit your target vocabulary size. What falls out of this process is a compression scheme shaped by the training data. Common English words become single tokens, common code patterns become single tokens, rare stuff stays fragmented. The target size matters a lot, and there's a real trade-off here. Take the word internationalization. A tiny vocabulary of a few thousand entries might split that into 6 or 7 fragments. A vocabulary of 100,000 entries might handle it in 2. Fewer tokens means the model processes your text with less work. fits more content into its context window, and costs you less per request. So the obvious question is, why not just make the vocabulary 1,000,000 entries and give everything its own token? The answer is that every vocabulary entry needs its own learned representation inside the model, which means a bigger vocabulary makes the model itself bigger and more expensive to run. And super rare tokens barely show up in training, so the model never learns them well. Modern models mostly settle somewhere between 100,000 and 250,000 entries. GPT-4o uses a vocabulary of about 200,000, roughly double what the previous generation used, and that jump alone made many prompts meaningfully cheaper to process. Here's where the strawberry thing comes in. People love dunking on AI models for saying there are 2 R's in strawberry. But once you know about tokens, this failure is completely predictable. The model doesn't see STRAWBERRY. It might see ester and AWI as 2 chunks, 2 numbers. Asking it to count letters is like asking you to count the letters in a word you've only ever heard spoken out loud and never seen written down. The letters literally are not in the input. Same reason models struggle to reverse a string, or write poems where every line starts with a specific letter, or do arithmetic on long numbers. Digits get chunked in inconsistent ways, so the number 3,529 might be 1 token, while 3,530 is 2, and the model has to do math across that mess. These aren't intelligence failures, they're plumbing failures. There's also a darker corner of this topic that I find genuinely fascinating. A few years back, researchers found strings like solid gold Magikarp that would make GPT models completely lose their minds. Ask the model to repeat that string back and it would insult you, or answer a totally different question. These got named glitch tokens. What happened is that certain junk strings, mostly usernames from a Reddit counting forum, appeared often enough in the tokenizer's training data to earn their own vocabulary entries, but that content got filtered out before the actual model training. So the token existed, the model just never learned what it meant. It's like a word in your dictionary with the definition page ripped out. Most of these have been cleaned up in newer models, but it's a great reminder that the tokenizer and the model are 2 separate systems trained on different data, and weird stuff lives in the gap between them. One more thing that has real business consequences. Tokenizers are trained mostly on English and popular programming languages, which means everything else pays a penalty. Text in Hindi, Thai, or Burmese can cost 3 to 10 times more tokens than the same meaning expressed in English, because those scripts get shattered into tiny fragments. Some researchers call this the token tax. So a user in Bangkok literally pays more per sentence and fits less into the context window than a user in Boston for identical API pricing. The same logic applies to code. Python and JavaScript tokenize efficiently because there's an enormous amount of both in the training data. A niche language with unusual syntax burns more tokens for the same 20 lines. It's a quiet structural advantage for whatever's already popular, and it compounds because cheaper tokens means more usage, which means more training data next round. So let me pull this together with what it actually means for you day to day. Your API bill is input tokens times the input rate plus output tokens times the output rate, and output tokens usually cost 3 to 5 times more, so verbose responses hurt way more than long prompts. Context windows are measured in tokens, not words, and a decent rule of thumb for English is that 1 token is about 4 characters, or 3/4 of a word, so a 128,000 token window holds roughly 96,000 English words, and a lot less in other languages. Every API response includes a usage object showing exactly what you consumed, and if you're building anything serious, log that number, because token waste is invisible until you look for it. And when a model does something dumb with spelling, counting, or arithmetic, check whether the failure lives in the tokenizer before blaming the model, because a lot of the time it does. Tokens are the one layer of this whole stack that almost nobody looks at, and it quietly shapes pricing, performance, language fairness, and half the weird bugs people screenshot on social media. If this cleared things up, subscribe, because I'm covering more of the fundamentals nobody explains properly, and tell me in the comments what you want broken down next. See you in the next one.